Hello, and in this video we're going to talk about a random variable and two different types of random variables, namely discrete and continuous. These will be one of the most fundamental concepts for the next sequence of videos. So first off, what is a random variable? Well, a random variable, which I'll represent simply by RV for abbreviation, is something that represents a measurement of a random sample or random outcome of an experiment. And let me demonstrate with an example. But before I do that, let us define the difference between discrete and continuous. So when I say a discrete random variable, so discrete means either finite or countable set of values or outcomes. And when I say continuous, then this is going to be an infinite or dense set of values or outcomes. And if you're not familiar with the word dense set, then that's okay, it's no big deal. Alright, so let us demonstrate with a few examples of random variables, and we will also determine whether they are discrete or continuous. So, example 1. Suppose we pick a random person in the mall and we measure their height and round to the nearest inch. And I'm going to define this variable to be equal to x. So what are all the possible values that x could take? Well, the minimum height that somebody could be is 0. The next possible height could be 1 inch, 2 inch. Yes, this is very small, but it's possible, right? And you could go all the way up to, say, 180 inches. I don't know how tall that is. But you can technically go up to 50,000 inches, right? Like a dinosaur or something. Right? But this is what we call a discrete random variable. Why? Because it's countable. That's why there's a difference between finite and countable. Finite means, you can count and eventually you will end, but countable means you can count, but technically you could count forever. So that's a discrete random variable. And these are all the possible values for x. So pretty much x is pretty much any positive integer in that sense. Sometimes we call that the domain of the random variable. So let's do another example. Suppose you pick a random person in the mall and measure the speed and record that time for which they can run a quarter meter. And I'm going to tell this, or I'm going to define this variable to be y, because it's technically a random variable because you're not sure exactly what the outcome is going to be, right? So what are the possible values of y here? So could somebody take and run it in 0 seconds? Possibly not, but who knows, it's possible. Could they do it in 1 second? It's possible, but highly unlikely. 2 seconds, 60 seconds, who knows? So is this a countable set? Because technically they could take, 1 billion seconds in theory. So is this a countable set? The answer is no. Because they could take 1.5 seconds Or they could take 0.5 seconds. Well, in that case, well, couldn't you count by 0.5s? Again, the answer is no, because you can take that and cut it up into even smaller pieces. So you could have 1.1, 1.2, 1.3 seconds, and even that can be, spliced up into even more smaller pieces. So that's pretty much what a dense set to some intuitive nature is. But overall, that is going to be an example of a continuous random variable. So continuous random variable. Namely, y pretty much belongs to the sets of real numbers. And it has to be positive, of course. You can't have a negative time, unless you're working time traveling or some crazy stuff. All right, so let's take a third example. So example 3. Suppose we play an arcade game. $50 times, and let z represents the number of times, how many times you lose. It's a random variable from at least somebody's perspective because you do not know how many times you will win or lose. So z is going to be equal to, well, you could lose 0 times. That means you win all 50 times. 1, 2, 3, all the way out to, worst case scenario, you lose all 50 times, right? But that's all the values you have. So, of course, this is a finite set. So if that is true, then that means z is a discrete random variable. Let's take another example, example 4. Suppose that, let's denote p is a random variable that represents the likelihood that it will rain. Yes, the probability of it raining is a random variable, of course. So p can range from 0 to 1. So 0 means it's impossible to rain. 1 being it will rain no matter what. You could also have, a 50-50 chance. You could have a 75% chance or a 25% chance, right? Now, what type of set is this? And remember, you can't go above 1 and you can't go below 0. So is this a countable set? Is it a finite set? Well, if you said yes to any of those, the answer is actually no. Because you can take these values and pretty much partition them into any categories, right? Because you can make that 1/8, 3/8, 5/8, and 7/8 if you want. You go to 16ths, you could take the square root of 2 probability divided by 2 or something. As long as that number is between 0 and 1, I don't care how many values it could have. So it could be equal to 0.137841326 infinite decimal, right? That's in between 0 and 1. That's no problem. But overall, this is an example of a dense set. Namely, there's infinite numbers that could fall between 0 and 1. That means what? That means P is a continuous random variable. And let us make a quick note here. So note, if x is a discrete random variable with many, and I'm going to put many here in quotes because this really depends on one's preference. If it has many values such that the distance between consecutive values is small. Again, small is subjective, depending on your purpose. Then, x may be treated as a continuous random variable. Let us illustrate this with an example. SAT scores range from 400 to 1600. And you can have decimal SAT scores. So I'm going to let S represent your scores. So this is going to be a random variable because technically you do not know a score for which a student will get, technically. So this value could be equal to 400, 401, 402, all the way out to 1,600. So there's quite a few values here, right? Namely, there's 1,200 values. So since these values are so many, the distance between them is going to be small compared to the total of it all, because it's going to be less than 0.001% between the two. Since those are really close together, and if I were to actually graph the frequency distribution of these scores, then these values would be really close to each other. And since that is allowed, pretty much there's a curve that's going to be passing through all of these curves, if that does follow some distribution at all, right? So of course this is our scores, and this is some frequency distribution on those scores. If the distance between them is really small, so delta S is approximately equal to 0, then that means we can treat this as a continuous variable. But of course, please note that this is a discrete random variable in its own right, but it can be approximated by a continuous random variable. And that pretty much can lead to a deeper discussion of when you should do this, when you should not, what are the pros and cons of doing that. But at least note that some people do treat a lot of discrete random variables as continuous, but please note that that comes with some error in calculations. But if there's many values, usually that error is very small and usually not significant for whatever applications there are. And that's pretty much the difference between discrete and continuous random variables.